Thanks everyone for joining. So I got this task of introducing protoplanetary disk, inner protoplanetary disk, of course. That's where planets form or planets migrate into eventually, right? So I will give you a brief kind of high-level general overview, which hopefully set the stage for, the talks throughout the week, okay? Okay, so here's the outline of the talk. So I will start by introducing you structures of inner protoplanetary disks, and I will introduce some important radial locations in protoplanetary disks, and what the reality is we figured out from our interferometric observations. And then I will move on to dynamics, and I will introduce some recent developments from MHD simulations, and I will talk a little bit about orbital migration under this new paradigm. Lastly, I will briefly touch upon chemistry of the inner disk and what we learned from James Webb observations. Okay, so this is a nice figure from Keith Dolman and John Monier's 2010 review paper. So we have a star, and then we have megalospheric accretion, which we can observe using hydrogen recombination lines or UV continuum. And then there's this little teeny tiny pure gas disk. We don't have dust, and I will get back to that point. And then at some point we have dust inner rim, and then eventually there's planet forming region beyond that, and I will go one by one throughout my talk. We also have the outer disk. This has huge mass, both in gas and dust. I love outer disk, but for the next 30 minutes I'm gonna neglect it, and then I'll focus on the inner disk. Okay, so let's talk a little bit about some important locations in the disk. The first is magnetospheric truncation radius. So that's where the magnetic pressure and the gas ramp pressure becomes the same, okay? So don't worry about all the, symbols and parameters, but the important thing here is that for a given magnetic field strength, given stellar radius, given stellar mass, and given accretion rate, you get to have something like 0.02, 0.04 AU, and of course you can scale things, right? The next is co-rotation radius. That's the place in the disk where Keplerian rotation, right, is the same as stellar rotation, okay? And if you plug in some numbers for a solar mass star, which is orbiting, rotating every 5 days, you will get something like 0.06 AU. So they are pretty close, and the relative location of these two are very important in accretion of the star, okay? The next one is dust sublimation radius. It depends on what kind of dust composition you are talking about, but it's about 1500 K, okay? And if you plug in solar luminosity, and if you assume it's 1500 K, you will get something like 0.07 AU, okay? So it's pretty close to the other two number, a little bit larger maybe. The last one is water snowline. Water freezes at about 170 K. So if you plug in again solar luminosity and the temperature, you will get something like 5 AU. So that's much, much further out in the disk, but that becomes very relevant and important in planet formation, and I will get back to that in the last part of the talk. So put things into context, we have already seen this diagram where planet masses are plotted as a function of orbital semi-major axis, and the number that we have been talking about this inner disk is 0.01, 0.1 AU, right? So we are looking at, things here. I'm not necessarily saying that those planets are formed in situ, and that's, one thing I will talk about when I talk about orbital migration. But, remember that this area that we are talking about is inner about 1 AU, okay? So in this diagram, that's about here. Okay. So let's dive into the inner disk observation. So it has a long history, but what made it possible is interferometric imaging. These days, it's done by VLTI interferometry, and CHARA. VLTI, as you can see here, there are 4 8-meter telescopes. You can also use smaller telescope at the same site. But it gives you angular resolution of about few milliarc seconds. So if you think about disks in nearby star forming region, which is about 150 parsec, it's going to be sub-AU scale, okay? 0.1 to 1 AU, okay? So that's very relevant to the size scale that we are talking about. Chara, it has 6 1-meter telescope. The maximum baseline is slightly longer than the other one, VLTI, and it's using visible and near infrared, so shorter wavelengths than VLTI, so that helps in terms of angular resolution. So you can actually get to sub-milliarc second angular resolution. So how does that work? I'm not going to go too much detail in technical stuff, but the thing is that we are looking at, we are collecting lights, and then we are looking at the correlated flux between different telescopes. So light coming through each and every single dishes, right? And then you see what is, received on this telescope, and you look at the correlated flux, and so on for all the other pair of the baseline. So that's what's called visibility you see on the y-axis. And if you plot that as a function of baseline, so that's the distance between telescope pairs, right? And you can learn a whole lot about what the emitting disk or ring or star, whatever you see, is like, okay? So the visibility, how it drops and how it bounces back and how much flux exists in the long baseline, that all tells you about the size of the rim, the sharpness of the rim, and how much flux is coming from unresolved star versus the disk, okay? Okay, so for the next few slides, what I'm going to talk about is results from VLTI gravity observations of Herbig stars and T Tauri stars. So there has been an ongoing survey where people looked at 27 Herbig AEB stars and 17 T Tauri stars. Okay, so when you look at Herbig stars, this sample on the left panel, you see, they measured the radius of the ring that you see, and its median value is about 0.6. This is the entire histogram, and of course you see some weird guys, 4AU, 6AU there too. In comparison, when you look at T Tauri stars, the median is only 0.16 AU. So if you plot everything all together, this is what it looks like. On the y-axis is the ring radius in K-band, that's 2.2 micrometer. Okay, and then on the x-axis is stellar luminosity in log scale. So these are T Tauri stars, these are Herbig stars. And there are 4 diagonal lines which, hopefully guide your eyes. So what you see is, okay, generally the rim radius, which is plotted on the y-axis, it's following L star to the 1/2 power, which is expected if the stellar luminosity is what's determining the radius or radial location of this dust rim, okay? Of course, there are scatters, okay? At any given stellar luminosity, you see a huge spread, and same for T Tauri star as well. So the question is, what's responsible for this scatter, right? And the other assumption that goes into this diagram is that the temperature is determined by stellar radiation only. So what if there's internal heating in the disk, right? And how does that change? People also looked at accretion luminosity matters or not. It turned out that a lot of these, most of them, accretion rate is pretty low. For T Tauris, that means 10 to the minus 9 to 10 to the minus 8 solar mass per year. For Herbig stars, it's usually 10 to the minus 9 to 10 to the minus 6, although there are some outliers. But overall, on the sample level, accretion luminosity seems to be negligible, okay? Now, this is a very nice diagram for T Tauri stars surveyed by this VLTI program. So what you look for here, what you look at is, okay, the triangles, this is the magnetospheric truncation radius that I introduced at the beginning of my talk. So that's where the disk is truncated due to the stellar magnetic field, okay? And you need to assume some magnetic field strength. In this case, it's 1 kilogauss, okay? And you see those are, within 0.05, 0.1 AU from the start, okay? This is the rotation radius, which is pretty close to magnetospheric truncation radius, but usually rotation radius is outer beyond the magnetospheric truncation radius, which is actually required for stable accretion to the star. Now, if you look at dust sublimation radius, if you assume 1500 K, you see this gray shaded region. Now, what gravity results shows is the dust ring radius, right, which is beyond generally magnetospheric truncation radius, rotation radius, as well as the sublimation radius. So we still have this picture. Overall, we have magnetospheric truncation here, and then we have pure gas disk, and rotation radius may locate within this pure gas disk. Thus, sublimation may happen somewhat closer to the star than what we see. So gravity results may actually see somewhat beyond the actual sublimation temperature. Okay, but still, again, overall, this general picture holds based on this observation. Now, you can also look at gas disk. So far, I talked about dust disk, but you can also look at the gas. In this particular example, people looked at bracket gamma emission. I must say that it is still unclear where bracket gamma is coming from. Of course, in the audience, there are a lot of experts, so feel free to chime in later. It can come from the accretion, but other than these two low accretors, where we see bracket gamma emitting area is much smaller or comparable to rotation radius and continuum radius, we believe most of this bracket gamma emission is coming from either the Keplerian disk or MHD-driven wind in the inner part of the disk. So right here, not necessarily onto the central star. Again, bracket gamma emitting region is generally smaller. So what you are looking at is here, yellow diamonds. And then if you compare that continuum, this is now dust rim location, which I talked in previous slides, right? Those are red. And you see consistently for T Tauri star, this sample, you see yellow closer to red, meaning that this gas disk, whether it's coming from Keplerian disk or it's coming from MHD winds, it's probing somewhat smaller radii than what we probe with dust, right? And these are for Herbig stars, and you can see that now this is the rotation radius. This is spatially unresolved, so it's called R-res, but this is basically probing the region where bracket gamma is coming from. So it's beyond rotation radius, right, which is consistent with this sample. And most of them is inward of continuum. So again, we see bracket gamma is coming from between rotation radius at some point here, and then dust rim. Okay, so that picture is still consistent between T Tauri and Herbig stars, and expected as this concept we had before. So if you monitor a star and disk over and over, this is actually great because if you think about outer disk, you study 100 AU, the orbital period is so long, 1,000 years, so you barely look at orbital motion or anything like that. When we talk about inner 1 AU, inner 0.1 AU, the orbital period is much shorter, so you can actually look at what's happening in, days and months time scale. And this is one of the attempts, right? So this is led by Ben. We just published the paper. So this data set is obtained with CHARA, one of the arrays that I mentioned earlier in 2019 from June and July. And if you look at this blue ellipse, and the location, it seems like it's orbiting. The data is not very good on this particular day, but if you look at it, it seems like it's orbiting, right? So you can determine the orbital period of this brightest blob in this system, right? So this cyan ellipse shows 0.13 AU distance from the star with proper geometry of the disk, right? And it turned out that the brightest blob is orbiting, the star at about 43 days period, right? And it's significantly longer than the local Keplerian orbit because we know the distance, because we know the stellar mass, we can determine the Keplerian speed, and Keplerian period is only 12 days. So it's significantly longer than Keplerian orbit. And if you were to find the location in the disk where you have 43 days orbital period, it has to be 0.3. So much beyond this, where this rim and this bright spot is located, okay? This is, of course, just one example, but there was another example on another Herbig star, HD 190073. Again, CHARA observation. There are only 2 epoch observations, but if you look at this bright spot, it seems like it's orbiting counterclockwise. And if you, again, measure the orbital period and compare that with Keplerian speed, Keplerian orbital period, this moving spot at 1.1 AU is orbiting too slow at that location. So if you were to find Keplerian location where you match the Keplerian speed, it has to be 2.0 AU. So, it's a little bit puzzling. So what is going on? There's another example. Now this time it's about outer disk. This is a system PDS-70. This is probably the only, or at least the most convincing example where we see planets embedded in protoplanetary disks. Okay? So you see here in near infrared, there are two bright spots, PDS-70b and PDS-70c. So we see thermal emission coming from the planet's photosphere. We see H-alpha line emission, again, B and C. So we know that the planet is accreting material. This is H-alpha line. And this one is beautiful ARMA image. We see the inner disk, we see outer continuum ring. And if you look at here, there's this blob, which we believe is coming from the circumplanetary disk around PDS-70c. Okay? What is interesting is that you see this asymmetry in the outer disk. So if you look at this continuum, you see bright spot here, not elsewhere. And we have multiple epoch observations in the same wavelengths in band 7 if you are in the ARMA business. And it seems like, well, it appears that that bright location is moving at the same speed as PDS-70c, so this planet here. So what this might be suggesting is that actually this bright spot, this asymmetry, is caused by this planet. And again, if you think about the two infrared example that I showed in previous examples, you needed something, the orbital location that's beyond where we see the moving spots, right? So it might be possible that there are perturbing body, whether it's perturbing the density, increasing the density, or increasing the scale height, or both. And then that frequency is matching to the planet's orbital frequency. So that's one fun speculation. Okay, so now moving on to the dynamics. Okay, so we still have this picture and simulations, although we have a lot of computing power these days and ever growing, but simulating an entire protoplanetary disk is almost impossible. First, it's because we are talking about 0.01 AU all the way out to 100 AU. That's 4 orders of magnitude in scale. But also, all the physics involved in is very different. You are talking about very different temperature, very different density and everything. So it's impossible. So I will split this into 3 sections. 1 in the inner disk where things are magnetized, ionized and magnetized. 2, transition around the inner rim. And the last one is magnetically inert dead zone. Okay? So this is a nice movie from Zawan, who will be giving a talk later this afternoon. So I'm not going to talk too much about this. But what you see here is magnetized star. It has dipole moment, and then there's magnetospheric accretion. And beyond the truncation radius, you see the disk is turbulent due to the MRI. So the 2 things that I'm going to highlight here are that the plasma inside magnetosphere, they rotate with the star. So if you look at this plot, this is showing the azimuthal velocity, so rotational velocity, as a function of radius. And here, 1 is the truncation radius. So if you look at here, right, the star and the disk material are co-orbiting, right? And it becomes important later in my talk. The other thing is that the inner disk is highly magnetized. If you look at this quantity, which is the ratio between magnetic pressure and gas pressure, if you're familiar with plasma beta, this is 1 over beta. And if you look at the numbers, this is 1, and this is 1,000, 110. So even beyond the truncation radius, beta is pretty small, right? Now moving on to the transition region. This is a nice movie shared by Mario, where he tried to set up a simulation. So you look at the dust density, and in this case, this is the temperature. And you see this nice rim structure. This is around Herbig star, so it's a little bit farther away, around 1 AU, but you see this inner dust rim. Now, what he has done is he ran this simulation, including magnetic fields, and see what happens, right? And you see the inner rim developing, and then there's dust trap, there's huge density jump here, and then there's dust is trapped here. One thing that is, I think, very important here is that the inner disk is MRI turbulent, which is consistent with what Jaehan's simulation tells you, right? So we show that this part is MRI turbulent, and here, what I'm showing here is the stress, turbulence stress, or alpha parameter, and it's about 0.01, 0.1, right? So it's MRI turbulent. Now, if you go into, beyond this dust sublimation radius, or more, in this case, the location where things are thermally ionized, alkali metals are ionized, the gas is not coupled with the magnetic field anymore. So there we call this is magnetically inert, dead zone, and the turbulence level there is pretty low because MRI is not operating, and the transition between MRI turbulent to MRI inert dead zone is pretty sharp. Lastly, this is a recent development in the field. How does the disk accrete, right? It turns out that when there's low ionization in this dead zone, now we are moving to the outer part of the disk beyond few AU, the ionization level is too low so that the material, the gas is not directly coupled to the magnetic field, but through non-ideal MHD effects. So instead of the traditional MRI effect that we have been seeing in the inner part of disk, it turned out that there's magnetically driven winds here near the surface. There's a planet, by the way. And the accretion is dominated through the surface region. So a lot of material is going into the inner disk, whereas in the midplane, things are pretty laminar. So if you measure the lane of the stress or alpha parameter in the midplane, that's pretty low. It's not as low as 10 to the minus 7, but also it depends on what kind of ambiguous diffusion number. It's a parameter in this setup that you need to assume. But it's pretty small, 10 to the minus 4. Again, this turbulence level will become important in the last part of my talk. Hydrodynamic instability, vertical shear instability, this is perhaps one of the most promising way to introduce turbulence in protoplanetary disks, but it's very unlikely to operate in this inner region because the disk is optically thick. What that means is that cooling is very inefficient, and under those conditions, VSI is pretty much suppressed. So we are left with pretty small alpha in this region where we think planets are forming. Okay, so we have all this planet population, and we talked about the dynamics of the gas in these disks, right? So how would these planets migrate or not in this disk? I'm not saying that they stayed there forever since they formed. They could have migrated in, and some of the planets, like low mass planets, terrestrial mass planets, can form after the gas disk is dissipated, right? But still, it's interesting to think about how they form, where they form, and how they might move around within protoplanetary disks. This is a nice plot that Alex created last week. So what this plot is showing on the y-axis is so-called thermal mass. Don't worry too much about the term, but what it tells you is whether the planet would open a gap in the disk or not. Okay, so if it's beyond 1, things become nonlinear, and it's going to start open a gap. And if it's 10, 100, 1,000, the gap will be wide and deep, right? So most of these discovered exoplanets, so what Alex did was basically, took all these values and then assuming some temperature distribution based on the stellar luminosity probably, and then converted this into thermal mass. And then you can see that things are pretty nonlinear. They will all open a gap if they formed in situ at the location they exist at current time, right? Okay, so these are all gap opening planets. So what would they do, right? I will move from the outer disk, okay? So as I said, wind might be dominating. This is probably the only simulation where people put 3D non-ideal MHD as well as planet, and then let planet migrate at this moment. So this is the state of the art. And what's happening here is that for a Jupiter mass planet, it opens a gap, but as you can see, the gap is pretty asymmetric radially, but also azimuthally, right? So here's where the planet is, and you can see the density distribution. This is very close to the inner edge, but far from the outer edge. So because of that density imbalance, what happens is that the torque from the inner disk is much stronger than the torque from the outer disk, and that's what makes these planets migrating outward. Okay? Now, if you move into the inner disk where things are turbulent, okay, let's assume that, somehow planet moves into this area, right? Things are turbulent. If your planet is low mass, if it's not opening a gap, it will do just stochastic migration because it's turbulent and you are seeing a bunch of turbulence, right? So that's pretty slow process, slow migration. If it opens a gap, it will be more typical viscous type 2 migration. That's slow, but, if you're talking about sub 1 AU, sub 0.1 AU, 100 orbits, 1,000 orbits, that's still pretty short time scale compared to disk lifetime. Lastly, if you put a planet inside magnetospheric truncation radius, right? Let's say somehow it happened, then what you will see is the gas that is very slow, rotating with the star, much slower than Keplerian speed, and that's the exact same plot that I showed before. And at that point, planet experiences very strong headwind, aerodynamic drag, and it can migrate inward. But if you plug in numbers and compute the migration timescale, it's very, very slow. It's 10 to the minus 8, so 10 to the 8 years, so that's 100 million years, and you see billion years. So it's very, very slow process for most of the parameter space. Okay, so I can speculate that, okay, let's form planet beyond water snow line, few AU, right? They form, we don't know what they do quite yet, right? They may migrate in or migrate out. They can stay there, still not clear. Many planets that manage to enter the turbulent inner disk, so this part, will migrate at type 2 rate because they are opening a gap, as I showed earlier. They are massive enough, okay? So they will migrate pretty fast. Again, type 2 migration is, known to slow, but at 1 AU, 0.1 AU, they don't take too long. So they will just migrate inward quick, within 1,000 years or something like that. If they don't open a gap, it will be stochastic migration. They may or may not migrate depending on what random fluctuation in density will do. And they might be why we see a lot of planets, low mass planets here, whereas we don't see a lot of them in this mass regime. And then finally, once the planet enters the magnetosphere, they likely stay there. Okay? So this is a rough view of what I think might be happening. So I guess I'm running out of time, and actually I'm not a chemist, if you don't know me, so I will pretend for the next few minutes that I'm Ted, and I will tell you what I learned from Ted last week. Okay, so of course James Bae is the thing right now. This is a survey of 4 disks where 2 of them is very compact disks. We don't see any outer disk or substructures. The other 2 are large disks with a lot of substructures. Okay, and you see all these lines. The thing that I'm going to talk about is the water. So what turned out to be the case is if you compare these 2, GK tau with compact disk, CI tau, large disk with some structures, right? Look at these ones, okay? They are mostly overlap with each other, the MIRI data. The black one, dark solid, is GK tau, the compact disk. The gray one is CI tau. And if you look at these ones, the blue ones, right, you see that the black one is above gray one. And if you subtract the 2 spectra, everything else is within noise, but you see that things are popping up at the locations where you see blue dots. So what are these blue dots and what are these red dots? So these blue ones are showing the high water lines that has low energy, upper state energy level that is below 4,000 K. The red ones are high energy lines with upper energy state of 4,000 K. So you need a lot, you need high temperature for these ones to excite. You need low temperature or intermediate temperature to excite these lines. And you see consistently, we see more of these low energy lines in compact disk than the other disk, larger disk. So the interpretation proposed by Banzatti et al. 2023 is that this enhanced cool water that has few hundred K in temperature with emitting radius of 1 to 10 AU, that's exclusively present in compact disks. So that suggests that there's a lot of icy pebbles drifting in, and then the water is evaporated in situ within the snow line, water snow line, and it moves up to the surface, and that's what we are seeing. The hot water beyond 400 K, it's seen in both disks, right? If you remember, if you subtract the two meteorite data, right, you don't see any leftover. What that means is that in both compact disk and large disk, we see pretty much the same level of hot lines, right? What that means is that, well, there's no difference, but these hot water, they can be generated through gas phase chemistry pretty efficiently. So seeing those comparable flux does not necessarily mean that there's something with icy pebble drift, okay? Okay, so there are some remaining questions. I will just go real quick because I ran out of time. Pebble drifts at the midplane, so you will have to somehow, evaporate those water in gas phase, and then it has to be delivered to the tau equals 1 surface, because we are talking about 20 micrometer, and 20 micrometer dust particles can loft up to few scale heights in this inner disk. So how do we do that? It needs some turbulence, and as I said, if you are talking about the dead zone, alpha is pretty low. So what is the source of the turbulence, right? Again, related, the chemical processing time at the disk surface for water is very, very short with extreme UV, so it's 100 years. So you need to keep supplying water from the midplane, right? So this is the rough number of icy pebble that you need. Rings and gaps appear to be common in large disk. And I'm going to just show you these beautiful images. We see all these rings and gaps. And I'm not going to go into detail, but the occurrence rate of these substructures in large disks are over 70%. So we see this everywhere. So how can we, mitigate that? Do we know, are we sure that substructures are not common in these compact disks, right? So that's a question that we cannot answer right now, but it might be interesting. The last one, I was going to talk a little bit about MHD wind, but basically what I was going to tell you is that MHD winds can help icy pebbles penetrate planet open gap from the work from my student. With that, I can also write a bunch of questions, but let me just show one question mark. How do we connect these things, observed planets and protoplanetary disks? With that, I will stop here and take any questions. Thank you.
Okay, so again, please go to one of the two mics or raise your hand if you would like me to come to you with a mic. And don't forget to identify yourself when you ask your question.
Hi, Paola Pinilla, UCL. I have a question about the Shara VLTI images that you show variability. I saw that, yeah, you highlight the rotation of these spots, but also it looks like there are some bright spots that appear and disappear. So I just wonder how much we can trust those, if you know. And also, you mentioned after that it could be a planet, but I wonder if the edge on the inner edge of a dead zone can create this kind of variability.
So for the second part, are you talking about inner disk that is well within this dust rim, or?
Yeah, so, yeah, I'm thinking about so where MRI starts to become from active to inactive, if we can have this, asymmetries and also variations and appear and disappear density.
Yeah, so if it was something in the inner disk that we don't resolve or we don't detect, it has something to do with precession, because the orbital period, it's just too long, so it can't be just orbital motion that's causing it, right? So it has to be inner disk that's precessing at very slow rate. I haven't worked out the numbers, and I cannot tell you a lot more. The other thing is on other features, and can we really trust that this blob is orbiting, right? Well, okay, I pretended that I work on inner disk, and I pretended that I might be an observer, but I'm not, as you know. And I think this is a good time to point that question to John Monnier, if you're here. Yeah.
Yeah, I'll be talking about the source later today, and we'll also sort of test the imaging, so wait.
Yeah, that sounds good. Great.
Okay. Thank you, Jack.
I have a question about so when you mentioned that you derived the parameter alpha for the viscosity, I assume that depends also on, there are some assumptions about the dust size. So I was wondering what dust size you're using or distribution, and if these results, how sensitive the results are to that.
Which alpha values are you talking about?
When you were mentioning for the compact disks.
Yeah. Right. This one?
Yeah.
Yeah. I brought numbers from the paper, Banzati paper and other papers. I didn't do the math by myself, but what you have to do is, okay, you can think about an alpha that will give you a diffusion, right? And then it will give you a diffusion time scale so that, if you put things in the middle plane and if you want to spread that out to 3 scale heights, that's about roughly where 20 micro should come based on the model they presented. So if you do the math, you need something very large. I guess, well, today's standard 10 to the minus 3 or bigger is large. Yeah, but that's basically how this number is computed.
Hey, thanks for the great talk. Stephen Jacqueline from Caltech. So you briefly touched on how planets might migrate through the magnetically turbulent region of the inner disk within the dust sublimation line. I'm curious how that migration might change as you move to even more massive stars that are less magnetized, and so you presumably get less turbulence there. So
right.
How does that migration?
Yeah, that's a really good question. So we know that Herbig stars has less strong magnetic fields than T Tauri stars. In that case, magnetic fields might not do a lot of work here. If the planet opens a gap, which I think should be the case for most of these exoplanets that we discovered, it doesn't really care whether it's turbulent or laminar. The time scale is comparable to each other. If it's much smaller than gap opening mass, it will depend on what the underlying density fluctuation is like. So if it's much less turbulent, then the migration time scale will be much faster because it's less stochastic. Yeah.
Thank you.
Yeah.
Jesse Christensen, Caltech. Can you go back to the slide where you have the compact disk and the non-compact disk and you subtract them and get the hot water? Yeah. So as you were describing it, and I was looking at the spectra, I was like, okay, so they both have hot water, which makes sense, and then the non-compact one has cold water, and then you said it was the compact one that had cold water. So I think I was too busy looking at it to understand the explanation. Why does the compact one have cold water and the not compact one not have cold water?
Yeah, sorry about that. That was me, going too fast at the end of the talk. But the idea here is that, let me go one more slide. So the idea is that if there are no structures, let's assume that the disk is smooth, then pebbles will just drift in, just because pebbles will experience headwind, because gas in Keplerian disk is, they rotate at sub-Keplerian speed. So they will always migrate in. If there is nothing blocking, they will just migrate in. If there are a lot of substructures, in this particular case, I'm talking about pressure bump, rings and gaps, which we do see with ALMA, in many of disks. This one in particular also has rings and gaps. If there's pressure bump, pebbles migrate in, but they are just trapped there and they cannot penetrate. They cannot move inward anymore. So that's what they propose. So there are a lot of gaps and rings in between before you reach the water snow line. So there are not much or any pebbles that is quoted by H2O that's penetrating this line, and there's no water.
Thank you.
Yeah.
I appreciate it.
Yes, on your last interesting, Ralph Pudritz from McMaster University, on the pebble flow into the interior and the detection of water there. Pebble flows can be driven by MHD processes, as you indicated, winds. Most wind theories think that the mass accretion of the star is driven at the surface layer, but Suriano et al. MHD wind models have pebbles driven at the midplane. So you wouldn't need a high turbulent alpha with that particular mechanism. And I was wondering what your particular theory is. You mentioned that you had a model.
Oh, yeah. So there was just very simplified model, and it's 2D. So what I did with my student is we used parameterized wind model. Again, we are not running all this parameter study in 3D MHD simulation. So just 2D, but you can parameterize wind based on how strong wind you have and so on, right? So given this wind strength, you can determine what the gas velocity is. In this case, again, we don't have surface or midplane. Everything is midplane, right? So gas velocity is now updated based on the wind strength, and then that will change the dust drift velocity as well. So what we found is that when there's no wind or weak wind, it doesn't really matter much, but if wind is very strong, it can actually help millimeter-sized grains or pebbles. They can penetrate in the inner disk. But yeah, again, this was a simple parameter study that is done in 2D, and the actual picture in 3D can be very different. But as far as I know, no one has done multifluid gas dust particles in 3D.
Lee Hartman. So I thought you were kind of suggesting at one point that in the inner disk for low alpha, almost anything can open a gap. And
can you say it again?
In almost any planet mass would open a gap.
Right, yeah.
So if that's the case, why, it's not really obvious to me why the compact disks couldn't have, if they have any planets in there at all, it seems like there's lots of them. Why aren't there pressure bumps? In the compact disks?
Yeah, how do you know if there are pressure bumps or not? Yeah, I mean,
you can't detect them, probably.
Right? Yeah, right now we can detect them, so we need to wait until NGVLA or ELT will come out and tell us.
So do they really have statistics on, compact versus non-compact disks, or is this, based on a couple of objects?
I don't think we have the resolution with which we can. For the water. Sorry? No, yeah. I don't think we have resolution to really tell whether there are substructures in the inner disk. When I say inner disk, which around water snow line, so it's going to be 1 AU, few AU, right? Yeah, it's too high resolution for ALMA. It's too far to do with interferometry, optical and infrared interferometry. So I think that's, yeah, that we don't know. But wait for a few more years or decade.
I will ask one more provocative question of our excellent keynote speaker. So, do you sometimes worry as a disk person, since we have both disk and planet people here, that the disk models are perhaps being led a little bit astray trying to explain the planets that we do see, and there's all these undiscovered planetary populations, as Jesse talked about, that could be just lying under the detection limit, including our solar system, that we don't see? Does that concern you? Do you wake up in a cold sweat in the middle of the night?
I mean, I am worried. Well, of course, we cannot detect like super Earth, mini Neptune in this protoplanetary disk. But what I'm worrying is, now this is going to outer disk, not necessarily the inner disk. But I'm worrying that we are not seeing any of these planets, protoplanets embedded in protoplanetary disk, except for maybe PTS-70 BNCs and a few other candidates. Yeah, I talked about this last week if you were here, but there are different possibilities. First, there are not planets there, right? The occurrence rate is very low in the outer disk, 10 AU and beyond. Maybe we are missing something about planet formation models. Maybe planets are forming very cold, not hot. That's why we don't see gamma emission. Maybe planets are creating episodically, which I think should be the case, just like young stars. And in that case, H-alpha or other hydrogen lines will be rare. But then the question is, why do we see H-alpha in PDS-70 system for both planets when the accretion rate is pretty low, 10 to the minus 8 Jupiter mass per year or something? But yeah, I'm worried about protoplanet detection in that aspect, regarding planet formation model, pretty much everything we are doing is a very smooth power law type disk model for both gas and dust. In the inner disk, again, we don't have an answer, but in the outer disk, at least we know that that's not probably true, right? So that's I think we need to make some modification.
Okay, with that, let's thank our speaker again.